Namaskar. Welcome to Dr. Mahanty. Sir, it's our privilege to have you today in Swatantra Bharat 75 talk. Kindly take the stage now and start your speech.
Thank you, Dr. Ranjan. Good morning, friends. This is an introduction talk, an interesting topic called modeling, simulation, and finding method in our engineering field. Why we are taking up this subject? Basically, from all the engineering institutions, whether we are studying our faculty or we are practicing engineers, we all deal with different systems, different products. It may be from non-engineering core sector also. When you try to understand how the system works and how to develop new products, the basic understanding of modeling and simulation and fundamental methods, especially for engineering fields, are very important in today's world. Next, maybe a 50 to 60 minutes time, we'll try to understand the basics, very simple basics of these three topics, of which modeling and simulation are gathered together, because they're kind of together. And the second is the finite element method, which is the part of extension of simulation, where also the modeling aspect does come. Now, before we start with the modeling and simulation, in the next 3-4 slides, we'd like to understand the system on which all this modeling and simulation, etc., starts working. So let's try to understand what is modeling and simulation. What is this? Basically, it is an unit or process which exists and operates in time and space through the interaction of its parts. So if you see bottom left side, a very simple sketch I made with the open system, boundaries there and surroundings, but there is input and output. So in this system may have one, may have two, or may have three, or may have four components or parts which will start interacting with each other and give some desired output. So that is the second definition. A system is defined to the collection of entities, for example, peoples or machines, that act and interact together toward the accomplishment of some logical end. So you get a definitive end which has got a important output. Now, when you talk about the system, the two complexity comes inside: a digital complexity and a dynamic complexity. The digital complexity is associated with the systems which have many component parts, whereas dynamic complexity associated with systems which have cause and effect separated by time and space. Certain things have happened for which the output may come after a certain time. The time and space will not be the same. It's quite difficult to deal with this kind of systems, but please remember, these are the things which is there in our day-to-day lives. And if you see the right side of the screen, you'll get all the examples which are in our day-to-day life. For example, in the center part, a fighter jet, right top corner, robo, automation part in the manufacturing industry, bottom middle is the space station, the great space, left middle is a bridge systems, like that. Different aspects are there. So look at this very engine systems. These systems have got definitive important output. It is not a weight. So there will be some input, some kind of working in between the whole system. They will be interacting with each other and will get out. For example, the top middle is jet engine. It does take as input a thrust of air, then mixes up with the fuels and give output thrust, for which the aircraft actually flies. This jet engine is used for aircraft purpose. Also, land-based jet engines are used for power generation purpose. Similarly, the bottom right is the metallurgical examples where the molten metals, steel especially, is come through a rolling and we get a rolled final products. These are all kind of engine systems where lot of inputs are there. They work together and give a definitive output. So this is the systems. So some basic terminologies when you start studying modeling and simulation as an advanced course later on, we come across this kind of definition or the terminal system, which is a group of objects that are joined together in some regular interaction and or interdependence toward the accomplishment of some purpose or an entity or an object of interest. It's not only in engineering area. If you look at the banking systems or look at other social systems, there's a regular interaction, interdependence from of each others, and you get an output. When you go to banking segment, which you go nowadays, it is no more. You do not go to bank, but you can do all the work from your home, and that is a system being developed for that purpose. Okay, so we get an output. Next, these examples. Next, attribute is the property of an entity. What is an entity? Basically, checking account balance, size of components or parts. Third is activity. Represents a time period of specific length and collection of operations that transform the state of an entity, an activity which gets changed over time and space. Example, making bank deposits, conversion of coal to energy. Third is event, which is change in the system state. How this whole thing is changing in this, for example, arrival, beginning of new execution, departure, etc. They are the event in a timely manner. State variables. They define the state of the system and can restart simulation from state variables. These are kind of your different parameters in this.
सर वो बीच में नीचे आ रहा है उसको डिसेबल करने के, कुछ ब्लैक आ रहा है ना, उसको
Skip
स्किप कर दीजिए और मैं उसको एक ही वहां पे देखता हूँ. विल कट दिस इन बिटवीन. अच्छा जा रहा है, बट व्हाई इट इज कमिंग अगेन एंड अगेन. आई एम ट्राइंग टू सी. Should not come actually. New caption. Make a question on the
okay.
No. I can delete. I can edit it afterwards. 1 minute. Sorry, ये जो बार-बार ये बीच में आ रहा है ना, I don't know why it is coming. It should not come. Skip. कुछ तो ये वाला ऑन हो गया. Turn on caption मैंने तो turn on नहीं किया है. Turn off क्या है? Captions are not turning. I know it's not there. Let us go ahead. Yeah, it's going well. और ऊपर आई तो ऐसा उसको skip कर दें.
Skip. I start from the last.
Same thing, sir. Let's continue.
State variables. They define the state of the system and can restart simulation from state. These are basically parameters. And here one should remember which are important parameters, which are primary or which is secondary parameters. The secondary in the sense which is dependent on the primary parameter. The secondary, they come into the picture when the primary parameters are taken into account and they initiate the interactions. Length of the job queue is the example of this. And this process, a sequence of events ordered on time, is a process. That's the whole activity. If you see the whole thing one by one, the attribute, activity, event, state, variables, and process. Process is the interaction of all the different components of the things. Here, the three concepts, event, process, and activity, they give rise to three alternative ways of building discrete simulation models. Now, let's see what is a discrete simulation. Before that, system state variables are a set of data. They require to define the internal process within the system at a given point of time. So, there will be a discrete event or a continuous event. Discrete event is basically which is changing at defined points called event times, which is not going to change over time. So, continuous event model, they're changing over time. Some of the system state variables like entity, attributes, resources, lists, delay. These are defined in this slide. Classification of systems is shown in this slide. Discrete event simulation system, stochastic and deterministic systems, static versus dynamic systems, discrete versus continuous systems. Basically, these are trying to show and display about a system where, again, the base concept of system is time and space, where if this is dependent on the time, it's changing with respect to time, the dynamic systems. continuous systems. So if it is not a certain point you are starting, it's called static systems. Some of the examples of systems, the practical examples, look at the power system. All are basically dynamic systems and continuous. Power systems you cannot have discrete, it has to be continuous process. Right? Bottom thing, if you see, is basically trying to show through a model how a motor power gets transmitted to wheel and tire for an automobile industry through gearbox system. So you can increase or decrease the speed, or you can stop. So here, it is I got a component in both static and dynamic aspect. Before we go to the end of things, let us see how we have contributed in this systems concept. Most of us may not be aware that in this country, we had great institutions a couple of centuries back, or millennium back, like Takshashila, Nalanda, Vikramshila, Vallavi, which have set very high standards of multidisciplinary research, teaching, and they have hosted scholars and students from across the globe. And these are things given in our histories. And in fact, now we come to know people are from far across European and Chinese and other countries, Japanese, they have come and studied in these universities. And these are now known through their memoirs. And this education system has produced great scholars, which name of some of them I just put like Charaka, Sushruta, Aryabhatta, Varamehra, Bhaskaracharya, and their contributions are enormous. What we talk about putting a great telescope in the space to study the space and do the calculations, some of them have done sitting on this earth and done a tremendously good accurate calculations. So they are model this. So this is now giving a concept of what they did. They actually developed systems and they've understood the basic different those parameters I talked about, like entity, attribute, process, and they could do different contributions in various fields like astronomy, metallurgy, medical, civil engineering, architecture, shipbuilding, navigation. I'll just touch in small point on this civil engineering and architecture aspect. If some of you have visited southern India and see those mammoth temples structure, and if you have read the histories, you'll be surprised that hundreds and thousands of tons big blocks were carried those days without having the modern train or the carrying capacity of big vehicles, and they have been built up. How they hosted and put it up, and which stood for last so many centuries. So these were possible because our ancestors they understood the different systems and how they interact and how they do that. So these are huge contributions that have been made by our people. Now let's get to the model. The system, when you talk about it, is basically an interaction of different components and parts to produce it. And what is this model? Model is a simplified representation of a real or theoretical system at some particular point in time or space, intended to provide understanding of the system. So, model is a basically toned down version of a system where we know the gross input and output or interactions at a particular time of its operation. It represents an object, a system, an idea in some form other than that of the entity itself. I've given some examples. Bottom left is a CAD model of treadmill bicycle. In reality, it looks much different, but when you try to understand, we built up a CAD model, simplified geometric version, and try to see how each component interact with each other for carrying load as well as for giving speed and without failure. The middle top is basically a wind turbine, how the whole things are connected and how they are interacting with each other for giving the desired output. Right bottom is very interesting finite element model, which is we'll talk in the last part. It shows electrical motor and how the winding has been and how they interact. Very intricate model. So these are possible today. In last about 3 to 4 decades time, we could develop this kind of systems. And let me emphasize here. From our country, we have contributed enormously in the field of finite element last quarter century or so. Different types of models are there. Again, please remember this model definitions depends on the time and space. So model types are also dependent on the time and space. Like continuous time and discrete time models, which is shown in the top right slide. Okay. If you look at this is a continuously going. What is the state pattern? Here is discrete in each time space. Okay. Every Friday, there certain things will happen because so many students will come and attend the course. Next is continuous state and discrete state. There is a state like each time spent by students in a weekly class or number of jobs in queue. For example, manufacturing industry. Then deterministic and probabilistic. Deterministic means you got a confirmed output aspect of this from the system. The probabilistic may happen like this. Because we do not understand the systems properly or have not been able to model the systems properly. Static and dynamic models, then stochastic and deterministic model. Other aspects are types of models, mathematical, physical, process. If you look at this, very interesting. Mathematical models because we could develop the mathematics and we have defined each of these components or parts and their input and output and the way they work and how they interact with other which are connected to these components and parts. We develop mathematical equations and algorithms and try to understand how they can behave in different functions. Physical models, which are basically real model, possibly toned down version, okay, a scale up or prototype kind, where we ignore certain things which are not very important to try to understand the system. Process models basically represent dynamic relations between mathematical and logical functions, and most of the time this third model is used in our manufacturing industry, chemical process, or where the time is very important from that. Different model classifications are there, like formal versus informal, physical versus abstract, descriptive versus analytical, hybrid descriptive and analytical models, domain-specific models versus system models. Different details are there, but we will not touch at this point of time. So, why need to spend so much time on talking with models? Because it can actually give, it takes a lot of time, but it will give you a kind of understanding of the system. It is a mathematical representation of system which allows simulation and analyzing the system, and they're never exact. And depends on the goal we are looking at. Are we trying to understand how they interact or what kind of accuracy we are looking at? Different. Most important, last point. Main goal of modeling in engineering is conceptual analysis and detailed simulations. These are two, whatever you try to do, understand. For example, you try to build up a tall building. Now we have to understand what kind of loading comes to the building. If you look at the loading comes to the building, self-weight, wind load, seismic load. Wind load comes with the total structure, seismic load comes on the bottom of the structure. So they conceptually try to analyze and then try to find out what kind of construction activities or the structural details we need to have. We need the detailed simulation for which we need a model, an engineering arena, but then we start giving all details things. Now the examples of modeling, simple process, chemical process modeling, piston engine modeling. Please remember, which is not going to show the details, but they're giving a representation how each of these component parts are acting in the system. So that system modeling is simple. Different types of modeling, like physics-based, finite element modeling, data-based. I'm not going to touch, this will be there. Hygiene-based, aggregate modeling, hybrid modeling, this is a little advanced, but I'm just mentioning. So these concept-based modeling, different varieties are there. And they're used in our day-to-day life for different applications. The modeling process. How you should start? Briefly, I will try to tell you. Let's see the step one is examine the problem. In this stage, understanding of the problem and selection of its classification accordingly, such as deterministic or stochastic, is done. What kind of type of modeling I need to do? Should it be very detailed? Should it be okay? I want to understand the behavior of the system. I do not go through the, or should it be dependent on time or independent of time? These are all things you care. Once we understand this step one, we go to the next step. Before we go to this first example, let's see simple things in our day-to-day life. For example, you want to get water in your tap. What I should do? I need to understand the water tank in the top of the building. But because how the water will go to the top of the building, there should be some water pump in the bottom where the supply from municipality comes. There may be storage tank. So this whole thing we try to understand. We give a sketch and find out how each are connected and who is impacting what. So then let's see the second step. Design a model. In this stage, performance of the following activities which help to design a model is carried out. As much as data you should collect. Analyze the system features. Determine the variable names, functions, its units, relationship, and the application used in the model. For example, I gave an example of water. What are the things which will be? A. The pump capacity which will be pumping the water from bottom to the water tank level. B. The size of the pipe. C. The number of output coming from this tank to different households, their sizes. So this will determine the force of the water, the amount, volume of water flowing there. So if I just understand what each component parts are doing their activities and functions and their units, I'll be able to do a better system analysis and can draw a good model to give it in good output. For example, all the households in the flat, the buildings will get a proper amount of water as they need. Then solve the model using a suitable technique and verify these results. Prepare a short report which includes results, interpretations, conclusions, and suggestions. How well improve if possible. And step 3 is provide recommendations after completing the inter-process related to the model. It includes investment, resources, algorithms, techniques, etc. Remember, I am mentioning an important aspect for investments. So far in both the step 1 and step 2, we try to understand the model, how they work. But if I am giving recommendations to go ahead with that, I also need to work on the cost aspect. Level of model is how much I should define these models. Define the boundaries of the system to the model, because that's very important. It should not be a open model, it should be closed. Whether a model is good or not depends on the extent to which it provides understanding. Some characteristics of the environment that is outside the boundaries may need to be included in the model. Not all subsystems will require the same level of detail. All the models are simplification of reality. Okay. Always remember, too little detail, risk of missing relevant interactions, and too much detail, overly complicated to understand. So these two last points are very important in modeling. It should be optimal, it should not be too less or too much, so that we lose our focus. Coming to the second part of this modeling simulation. Now we try to understand the system and how do I model the system, because we did not get the total model. What is the important aspect of that model you made? Now, after making the model, we need to simulate it. Why you need to simulate? Just to understand the interaction of different components or parts of the system and how they give the desired output. Are we looking at that kind of output, or are we looking at something else? So to do that, instead of making a physical model, we try to simulate through different methods. It can be broadly defined as a technique for studying real-world dynamical systems by imitating their behavior using a mathematical model of the system implemented on a digital computer. Now, if you have asked a question, the same definition of asked, maybe 3 or 4 decades back, the last word, digital computer, would have been not part of this definition. Why we are putting this digital meaning? Because nowadays, to enhance the capability and also the accuracy, the computers have been used in our daily life. It is very much part of our system, the human system. So this is important to understand. Simulation of the system is the operation of a model, which is a representation of the system. The operation of the model can be studied, and from this, properties concerning the behavior of the actual system can be inferred. How they behave, how they interact. The model is amenable to manipulation, which would be impossible to, or too expensive, or too impractical to perform the system which it portrays. There are 3 important points you should remember. So, it can be said that simulation is simulated systems indicates operation of the actual system over time. Artificial history of system can be generated and observed. Internal, perhaps unobservable behavior of system can be studied. Timescale can be altered as needed. I need not wait for all the, suppose the process taking place of 6 hours. Just to understand the system model, I can run it for a couple of minutes to understand. Conclusion about actual system characteristics can be inferred as actual system is compared to simulation. Now this is simulation. Why it is required? How to use it? It enables us to perceive the interactions that would otherwise be apparent because of their separation in time or space. Though it is just 1.5 line sentence, but very bit. If you look at any kind of process, for example, look at a very complicated process of thermal power plant or any power plant. If you look the whole power plant as a single entity and see how the input starts and how the different activities carries over that, and finally we get output as a power in our homes or our institutions or our factories, we never look into this power generating systems. So it's quite apparent, we accept it, but it's a very interacting phenomenon of different components, parts, subsystems. So how to use it? Simulation. Develop a model, simulate it, analyze the results, learn from the simulation, revise the model and again do the simulation, continue the interaction until adequate level of understanding is developed. That's why the simulation is important for us. As I give the example of the power plant, how do I enhance the power factor or how do I enhance the availability of power over a constant time? And give an example of hydropower systems. Hydropower systems, we look in night time, the requirement of power in our society is quite less compared to the daytime. Because a lot of times the office will not work in the night. So that power requirement, how do I now maintain that continuity and the consistency of the power generation? So that's why we need to have a proper simulation system. Classification is based on continuous simulation and discrete simulation. It's a simple word is over the space of time, and time and space it is carried over, whereas discrete is over the event given with particular time of applications are there. Different applications, if I look at our Indian systems, design and analyzing manufacturing systems, evaluating hardware and software requirements for computer systems, evaluating new military weapon systems or tactics. In fact, a lot of war games have been developed over the last 2-3 decades, where how do I use different systems and tactics to overcome the difficulties in terrains or the environment. Determining the ordering policies of an inventory system, designing communication systems and message protocols for them, and which is this fifth one, it is very apparent in the modern day life. You look at the social networking and social systems we develop through this communication system. Last one, but not least, design and operating transport facilities such as freeways, airports, subways, ports, which is basically for facilitating us from traveling from one part to another. Then distributed system simulation, continuous systems. Again, this all depends on the kind of time and scalability you are looking at. Now, next 2-3 slides we'll be talking about the again types of simulation with respect to different entities. It's live simulation, virtual, constructive simulation. Live is the real-time systems and actors, real environment. Whereas virtual is virtual systems and actors, virtual environment. Constructive simulation is virtual systems and actors, virtual environment. Okay, it's basically to do measurement, comparison, forecasting, and concept. With respect to time advance is discrete and continuous. We have discussed about this time and space concept earlier. So based on those, the two simulation types of discrete and continuous. With respect to result, output, types of simulation is deterministic, stochastic, traditional, agent-based. Some of the examples, last point I'll touch. Vehicles and pedestrian traffic situations. Most of us may not be aware that big cities, these are very important aspects. Cities like Bombay or New York, where the vehicle movement will be made in such a way, the simulation will be done in such a way that minimum time is spent by people from traveling from point 1 to point 2. Then actors in financial markets, consumer behavior, humans and machines in battlefields, people in crowds, animals or plants in ecosystems, various examples are there. And these are examples based on this 4 types of simulation based on results. Basic component concepts of modeling simulation. So we understood the basic concepts. What's the modeling, what systems and simulations. Manipulation of modeling in such a way that it operates in time or space to summarize Object is an entity which exists in the real world to study the behavior of a model. Base point is a hypothetical explanation of object properties and its behavior, which is valid across the model. It will not be changing at any point of time. System is the articulate object under definite conditions which exist in the real world. Experimental frame is used to study a system in the real world, such as experimental conditions, aspects, objectives, etc. Lumped model is an exact explanation of a system which follows the specified conditions of a given experimental frame. The last 2 points, verification, validation, a very important aspect in engineering pyramid. We use these words very often, but sometimes we do not be able to understand what they mean. So verification is the process of comparing 2 or more items to ensure their accuracy. It can be done by comparing the consistency of a simulation program and the lumped model to ensure their performance. Whereas validation is the process of comparing 2 results. It is performed by comparing experiment measurements with their simulation results within the context of an experimental frame. The model is invalid if the results mismatch. So if you see verification, it is with the lumped model, and if you see validation, it is with the experimental frame. So these are the basic concepts of modeling and simulation. Developing simulation model. System entities are input variables, perform measures, and functional measures. Basically, they are all connected. In step 1, we try to identify the problem with an existing system or set of requirements of proposed system. Step 2 is design the problem with taking care of the existing system factors and limitations. Next step is collect and start processing the system data, observing its performance and result. Step 4 is develop the model using network diagrams and verify it using various verification techniques, as I mentioned. Step 5 is validation. Validate the model by comparing its performance under various conditions with the actual systems. Then create a document of the model for future use, which includes objectives, assumptions, input variables, and performance data. It's important to know that step 6 is important because someone will come in the future time frame and start understanding and with the change input variables how the system or the whole modeling simulation is going to behave. Step 7, select an appropriate experimental design as per requirement. Step 8 is induce experimental condition on the model and also the results. This last 7 and 8 is physical entities to understand how our simulation has gone ahead. Let's keep this. The importance of simulation cost aspect. It is safer and cheaper than expensive real world systems. It can be more realistic, can be conducted with the real expenses out of reach. I'll give you some examples of this. Some of them are like biological systems. If I ask a question, how much blood are human beings having? I cannot cut a person, drain out the whole blood and say this is this many liters. I can actually model, simulate, and find out the approximate. It's not a deterministic but kind of probabilistic way to say this much blood is there in the system. So it will be quite easy, and this is simulation being important from there. It provides an integrative synthetic environment for analysis, testing, and training. Cost aspect of a simulation only in terms of software package price is wrong. We should not go further. Let's see the output it gives and how it is impacting our time saving and kind of weeding out which is not important parameters. This is the part we normally do not understand or we ignore in our simulation aspect. There are actually at least 3 cost aspects of simulation. Purchase price of the software, programmer understand, timeliness of the results. If the result comes in time, how is avoiding issues? Example for this, timeliness of results. For example, if you look at 30 years back, a lot of time in our eastern coast of our country, we used to have a lot of loss of lives due to the natural calamity. But over the time, when we started simulating, we are giving a lot of time good results and in timely results, so that a lot of people can be evacuated when the natural calamities comes, like heavy rain or flooding, etc. So this is important for us to understand the simulation. Steps in model and simulation building. Define an achievable goal, very important. We cannot do without any. What we want to achieve, we need to understand first. Put together a complex mix of skills on the team. Complete mix of skills. It may be only engineers, it may be users, it may be producers, the people who are manufacturing, it can be suppliers, everybody. We must involve the end user. See, I put a separate point for end user. How end user should feel. I'll give an example from engineering area as well as non-engineering. You go to a bank, and if you are not satisfied at the bank, why you are not satisfied? You are not getting your action of taking money in time or will to transfer money from one account to another in time. So your end user input is very important. Choose the appropriate simulation tools. Very important from us. Is it a discrete event or is it a continuous event? Is one time in over a span of time or is it continuously happening? Model the appropriate levels of details. How much detailing I need to have in this whole simulation? Because if I go ahead and understand that these are important parameters, these are not important parameters, I will be able to model it much accurately than if I do not take into account those issues. Start early to collect the necessary input data. Very important. For example, if I collect the data of the banking industry over the aggregate time of 6 months to a year from many people, then I understand the variety of the requirement and applications. If I go and spend only 3 days or 4 days and try to understand, I will not get the details. Provide adequate and ongoing documentation. This is a very important aspect, especially in engineering domain. We need to have this documentation aspect very clear. I may have done a simulation, I must keep that record. If I change tomorrow this simulation aspect or some modeling aspect, I should also keep that record so that we can understand how much impact it has been made. You develop a plan for adequate model verification. Are we getting right answers? Very important. Similarly, develop a plan for model verification. If we ask the right questions to get the right answer, so these two plans are very important. And develop a plan for statistical output analysis. When I get the output, how do I analyze the data? I'll give an example. Transport systems. When we talk about transportation, we think about vehicles. Looking that, remember the pedestrians movement or the vehicle movement over a road, a crossing, how much you can do. It will be statistics output. How do I analyze this statistics output? Is it very thick traffic movement during the morning hours or evening hours? Based on that, we can say, okay, this is a one-way traffic or this is a two-way traffic or what kind of interaction should. What advantage we get using modeling simulation? It's easy to understand, easy to test, easy to upgrade, easy to understand constraints, easy to diagnose problems. These are the 5, 6 very important advantages by using modeling simulations. But some disadvantages are also there. Because first disadvantage, designing a model is an art which requires domain knowledge, training, and experience. The person who has not got a adequate training or domain knowledge, for example, who is not a space scientist, he does not understand the domain, so he cannot do a model of spacecraft. Operations are performed on the system using random number, hence difficult to predict the results. Third point, simulation requires manpower. It is a time-consuming process. We need to have proper manpower training who can do this, so it takes time. Sometimes simulation results are difficult to translate. It requires experts to understand who can give them output and define. It sometimes is expensive. But this last point, though it's debatable, over time period, this is becoming less expensive because of the growth in our computer hardware and software. Different applications areas we have mentioned, but still briefly trying. Strongly reflected in our medical research, training and support, industrial engineering design and presentation, like factory process design, manufacturing. We have done a lot of projects in these areas. The complete factory process has been designed and output has been, productivity has been increased tremendously. Civil engineering design and presentation, like building design, I mentioned city and infrastructure planning, like travel, transport systems, etc. Mechanical engineering design and presentation, like engine designs, aerodynamic design for vehicles, for the aircrafts, for different aspects. Natural sciences, physics, chemistry, biology, meteorology, astronomy, many more applications are coming up. Geographic information system, GIS, Earth modeling, this modeling, and this is very important because today, from this modeling, I can find out how much long cable I need for laying down power cable from point A to point B if I have GIS. Militarization support, I mentioned war modeling, deployment, etc. Training like simulators, games, very important. One example I can give you, the aircraft pilot training or locomotive pilot training. Now, no more the people are going actually on the aircraft and they actually being trained on the simulators, where they get the same feeling like sitting on the cockpit or sitting on the aircraft local engine. Entertainment games are big important aspects which is impacting our day-to-day life in different. All of us play the advanced phone sets by playing different games. So these are the kind of application areas. Limited I've given, but the examples can be running in many. Now what we have given in India's contributions, briefly only one slide I'm mentioning, which is open to knowledge. SAM cluster under DRDO undertakes modeling simulation system analysis for the purpose of strategic, tactical and operational decision making in defense and defense arena. Very important. They have developed a lot of subsystems. ESA, which is a part of system analysis modeling and simulation for various defense applications, particularly deployment, tactics and force potential evaluation, tactical strategic mission planning, etc. Part of our defense systems. Division of Forecasting and Agricultural System only of ICR. ICR stands for Indian Council of Agricultural Research. They deal with very important aspects of modeling and research in forecasting the agriculture output, environmental phenomena, because that will give us a good impact on food grain. And if you look at the India's contribution food grain growth over the last 20 years, you'll see a tremendous thing happen because of their proper forecasting agriculture system. To upgrade the forecasting coverage of various programs, basically for the climate condition. The Ministry of Earth Sciences, they have developed across, which is atmosphere and climate research modeling, observing systems and services. Today, we have, if I'm correct, almost 86 parameter modeling forecasting systems have been developed by India, and we are in a position to quite accurately develop forecasting of various climatic conditions. National Center for Medium Range Weather Forecasting is a center of excellence in weather climate modeling under this Ministry of Earth Sciences. The mission of this center is to continuously develop advanced numerical weather prediction system with increased reliability and accuracy over India and neighboring regions. That's the reason, if you look at over the last decade and a half to 2 decades time, our loss during the natural calamities are much less. Now, ladies and gentlemen, we have more or less tried to get into the modeling systems. So some pitfalls are there which we need to guard against, which is briefly told about. We need to be very careful that we need not go through certain things like objectives should be clear, your input should be proper, model should be proper. We should not go for undocumented assumptions, it should be documented. Wrong input should be avoided. Replacing distribution system by its mean should be avoided. Wrong performance measures should be avoided. Poor schedule and budget planning. So these kind of things are there which need to be avoided to guard against this. This is a part of the problems we face. Now, a link before we get into the entanglement concept. The model is just trying to capture the whole things what we covered in the last about 30 odd slides. Model is a task-driven, purposeful abstraction and simplification of the perception of the reality. This is the model. Concept. Simulation is the implementation of a model. This is simulation. Symbolic. So implementation. And this is a system. So they are all connected. These two are directly connected. System and simulation is a dotted connection. This is a link actually in this symbolic. Now, having said all this modeling and simulation, how finite element is connected to this? Very important. The finite element is a simulation soft tools which developed about 60 odd years back by engineers. Why? Let's see what we have in our real engineering field. Real engineering field, we can say we have 4 things: a field, an action, a reaction, condition. If you remember at the beginning of this modeling and simulation, I showed this slide. An open system, it's got a boundary, some input is coming, some output is coming. And this is a system. And what are the slides I showed in the first, second, third slides? If you look at those products, each of them is called a system because there are some input and some desired concrete output comes. How do I now? We talk about giving some input in the system and getting some output. I have to analyze the whole system. How do I analyze the system? That analysis aspect is developed, or simulation is developed based on this concept of handling method. So it's called FARC. A field is there, with some actions given, some conditions like how it is held, because it cannot be just floating around, and some reactions. So if you try to see those examples of a jet engine, it is connected. Either it's based on the land or it's connected to the aircraft. There's a condition, it's fixed. And some input is the actions on this whole system. And I am getting output. So I am giving some air and some fuel, it's getting burned, being compressed air and turbine, and getting output is a thrust. And the aircraft is flying or power is getting generated. So this is what we have in an engineering field. We have a system where we got some field. There's a field actually. We got some input, this action. We get some reactions, output, and some conditions. How it's held. So normal engineering design. I think engineer will see. This is my physical problem. Modeling also you see this physical problem. I bring it down to mathematical model. And we give some assumptions like in a mechanical or structural engineering, some geometry, kinematics, material, etc. Questions regarding the problem. How large are the deformation? How much is the heat transfer? Etc. So many things will be there from different perspectives. So physical problem is brought down to mathematical level, which is being governed by set of differential equations. Here I'll speak about 2 or 3 sentences differential equations. With these differential equations are basically an interaction of different parameters with respect to time and space. And these are important for dynamic systems. Most of our application engineering domain is dynamic systems, which is dependent on time and space. So these are the differential equations which define how each parameters interact with each other to get the desired output. A little modifications we do. What is that? We have done physical and mathematical. To enhance the capacity, we developed numerical model. The selection of the mathematical model depends on the response to be predicted. And most effective mathematical model is the one that delivers the answers to the questions in reliable manner with least effort. Numerical model is as accurate as mathematical model. Because what we do, we differential equations we convert into a set of algebraic equations. That in any finite element method we try to understand, it does that job. So, modeling a physical problem. We got a physical problem, mathematical model, numerical model. Did I get the answer? Is the answer yes? We have. If it is not, refine the analysis, improve the mathematical model. Or I want to change some design improvements, structural optimization is one aspect. I go back and change the physical problem. So this is cyclic improvement. Until the time you get a desired output. This is a modeling a physical problem. So there is simplified fashion I am talking about. So what is final method? Method for numerical solution of field problems. So what is field problem? Basically, defining a system or a field with a set of differential equations. Okay, like for example, it's a governing equation, differential equation. Elastic problems, thermal problems, fluid flow, elastostatics, different. If you look at this kind of problems we are defining, these are basically when you see any example of our engineering domain, you'll see these are the basic problems you encounter. Thermal problems, for example. Now look at the power plant. We want to find out how much heat transfer is taking place. This is a thermal problem. So we develop a governing equation with some boundary conditions. Okay. Like boundary conditions, for example, in thermal power plant, what kind of conditioning that input is given, what kind of condition the output is coming, how the whole system is for creating that output is happening, those are things. Some examples of these questions I am giving you. Like structural heat transfer, acoustics, fluid flow, nuclear fusion, universe. Last one is from physics field, Einstein's field equations. And if you look at all these equations, the differential equations, and these are important because, as I mentioned in my modeling and simulation aspect, a system is most of the system in the engineering area is basically dynamic systems. They are changing with respect to time and they're interacting with each other. They're not isolated or independent. They depend on each other. So basically, integral and differential or algebraics are used for formatting final element. This is a simple structure. I am modifying this. I'm simplifying geometry. And if I see, I'm having this kind of domain, unknown function field variables, discrete values. So a continuous system I can put it in a piecewise approximation function. Why I do that? Basically to understand and also get a quicker answer for this. Most important aspect of this method, it can adapt to different types of problems and boundaries. This first example, all engineering students, irrespective of the branches, have gone through this calculation or simulation of cantilever beam. I apply a load, how much deflection happens. We got a mathematical equation for it. And when I do a model, this is my modeling aspect. I simply a mathematical model I try to do, I'll get an equation, but if physically I want to see this is my mathematical model. Two-dimensional I modified. This is my field. This is my boundary condition. These are my output. I can create a mathematical model. This is three-dimensional. I can create a three-dimensional model. So this adaptivity of types of problem boundary is important for us. This is captured in this slide. Physical system, mathematical form, solution, numerical analytical. What kind of solutions we use? Types of solution. What parameters we are interested in. Now, why we need these parameters? Who is using these parameters? As an engineer in different fields of engineering, if you look at the output we are talking about, it gives like displacement, strain, any kind of civil, mechanical, electrical engineering you do, any kind of components and structure or system develop, we need to understand what kind of stress, what kind of strain. Depending on that, how long this component or structure will be sustaining or product will be sustaining. We talk about, for example, a bridge structure will be sustained for next 50 years. How I calculate that? When we go through the structural analysis and we find out the displacement, stress and strain, we based on that we find out how many cycles of the stress and strain will be able to adjust till the structure fails. So 50 years, 60 years, sometimes 100 years. Second example, heat flux, temperature. For example, in a power plant examples I gave you, how long it will be taking. So what level of accuracy I'll get, what kind of power output I'll get. So different examples, sir. This is the whole explanation is been made from physical system to parametric system. Why this is superior over other numerical methods? Any kind of complex domains can be put to use by final method. Over each element, algebraic equations among the two countries of interest are developed, not differential equations. That means it is definitive answers I'm going to get. Different types of metal properties can be used. It's not only isotropic, many kind of change. And please remember, multiple elements can be joined together with multiple types of element properties we can analyze. I can actually get much accurate results by using more number of elements or variety types of elements. And all these elements are assembled using inter-element relationship. This is well developed. Now, what's the impact of the computer on development of API? I'll give briefly before we start going a little further. This finite method got developed because of computer capability development. We know the basic mathematics, but to calculate that, we need a lot of computing power. If computer would not have been developed, this method would not have been seen the day after. I'll give an example of kind of publications which we had in 1960s, early 60s. Only 5 journal papers used to come out in a year, 5 to 10. Now, in the 4 to 5 decades time, every day, almost 50 to 60 journal papers are coming out in different field applications. This is all possible because of the computational capability increase. The behavior of a system or phenomenon system depends on geometry, domain of the system, property of the material, medium, boundary and initial conditions. These It can be domain, can be very complex, bond loading can be. So numerical methods has been developed so that I can get a different better results, and this is possible through the computational power developed over the time. This is capturing the whole finite method analysis. It's the analysis part, not a method. Governing questions, bond dependencies, approximating I do, I get this output. And this has been converted into matrix form to get the things. Different types of properties, behavior, actions we can get from it. A simple example. It's basically a simple, see, look at the actual geometry. I want to analyze this. So I simplify, I remove this kind of holes and simplify geometry. And then I make a finite element model and get an output. It's a numerical technique which is a continuous field is divided into or discretized. The right word is discretization. In normal language we call division. Well, elements. They're well defined. Well defined in the sense their boundaries are well defined, their behaviors are well defined. Okay. Though they look like a simple triangular, quadrilateral, cubic or cuboid. So as the result of this discretion, the original field would indulge infinite degrees of freedom. If you look at many points are there in the whole field, which has been converted into these points connecting the each element. And then I can analyze this finite number of points in a from infinite area to finite. That's why it is called finite element model. This is a system which is some cutout. These are system boundaries. I have converted into a finite element model. So these are basically nodes which is connecting to different elements, and all the action and reaction happens through these nodes. So I have a limited number of nodes to be addressed. So I got much more better. Now accuracy of a problem and accuracy of output depends on the way we discretize or we define this whole system by appropriate type of elements. So this whole thing is called mesh. These are each individual is called finite elements, and these nodes means connecting points through which each element is connected, and all the interactions happens through these nodes. So when you apply a load in real system, the application of the finite element model will be on these nodes. When you get the output over this length of this domain, I get output on these nodes, and I can of course generalize that this is my real location. Now, before you go, elements. What kind of elements? Zero dimensional? Yes, possible. It's a mass element. I want to show a mass, which will not show any geometry. For example, I'll give an example of this. Locomotive engine. I want to understand the basic load carrying structure of the locomotive engine. I do not do the superstructure of the locomotive. I can consider as a mass, which may be running in a couple of tons. So I can consider the mass element, which will be having only mass as an entity, but no geometric dimension. One-dimensional elements only extend in their one directions, used for various purposes, covering the line. Two-dimensional elements basically covering the area. If you look at the different things, here in the 4 nodes are there, 6 nodes, 8 nodes, 9 nodes. Here 3 nodes, 6 nodes. These are basically higher grade of elements, which will try to depict much more nonlinearity aspect along the lines. Like get a better picture of the behavior of the system through simulation. Now, 3-dimensional elements is basically trying to show you the different volumes. So, in effect, through the concept of this finite element, I can capture from 0 to 3-dimensional any kind of objects here there. An example, simplified example of different types of elements, rod and beam elements, very widely used for building structure construction, basic analysis, membrane shell subjects, for example, in power plant, like pressure vessels, heat exchangers, all those things. Brick elements takes for showing the solid calculations, and some spatial elements, strain, gap, any kind of problems what we have in our real life, we can actually show them to these elements and the connectivity. They are basically selected based on the geometry and analyst experience to optimize computational efficiency. So you need a lot of experience also to start. Now, some of the steps. First, you need to do a geometric modeling. For example, this is actual crankshaft. And if I want to model this kind of surfaces, two base surfaces, this is the actual surface. So I blend it. So to get an idea, because these are stress reducer. If I keep this kind of surface, I'll have a high stress in this area. But if I blend it like smoothing out, I'll get a lesser stresses, which is actually there. That's the reason in a mechanical systems we do not keep any kind of sharp edges or contours. Discretization of continuous meshing. How I create a mesh, Feidelman discretization using these different types of elements we talked about 0D, 1D, 2D, 3D. A plate element, through plate I am discretizing, and 3D objects, how I discretize, see that. Okay, these are solid elements. Important aspects of this Feidelman measurement. Problem type. What is the type of problem that we find? Shape function. Shape function is defining the behavior of each element. How they behave, linearly, quadratically, cubically. Why we need this? Basically to see the output. In a simulation, we understand that how much output is I look at, what kind of output you are looking at. So depending on the output you look at and the accuracy, the shape function of element is very important. So type of element, different types, area of interest. And how do I control the mesh? Submodeling, fracture modeling, adaptive meshing. Let me tell you, in India, this submodeling has been given enormous impact by Indian scientists and engineers in 70s and 80s. When we had, why we did this? Because computing capability was very limited those days. That's why Indian contribution submodeling is world famous. And most importantly, a lot of Indians are involved and they gave new techniques and capabilities. Different types of material properties you can put. Like some examples I'm giving from structural analysis and thermal analysis. These are kind of material properties we need to have. Okay, to get it. Now, from a perspective of an engineer, we understand these material properties. But from an end user perspective, what they'll see output. If I'm using, for example, a power plant, how long it will be operating in a sustainable manner. To do that, I need to understand what kind of thermal conductivity, material properties, density, vapor pressure, trip strain, different type of output or inputs are involved in the modeling and simulation aspect. What kind of boundary conditions? This is the boundary conditions, like how the whole system is held. It will be fixed boundary conditions, like pressure vessels, it is fixed standing in a place, a bridge standing in a place, a building. Variable boundary conditions, like for example, you're going with aircraft, you're going in a plane or a train or vehicles. The boundary conditions are changing. There's a structural aspect, thermal aspect, you can see a fluid flow. Okay, flow is happening from one point to another point. It is losing its temperature, it may lose its pressure, it may lose its velocity, like that. And some contact, friction boundary conditions. In these 2 points are very important: over constraint and under constraint. We should not over constrain the whole system. Then it will redundant supports. Excessive constraining will not be able to give us a correct model. It will be very stiff. Under constraining also, it will be very bad because it may lead to rigid body movement. That means what we look at will not get. What kind of load comes to the systems? So physically, if you look at the kind of loading comes, for example, in a vehicle, the load comes from the tires, and basically self weight of the vehicle and moving load. How do I transfer those loads? It will be transferred through nodal points. Element load like pressure, thermal, inertial forces, time and frequency depending different loading. Like when the vehicle is moving, the point on the tire is experiencing cyclic loading. Depends on the speed of the vehicle. It can the same point come and get in touch with the earth or the surface is moving over in maybe in 1 second, maybe 10 seconds, depending on the speed of the vehicle. And that will actually tell me the simulated results. So very important the loading conditions. When I do the solutions, I get the output. What output I get? Whatever I need to get, like thermal, temperature, pressure, or structural. And these are important for system simulations and output results. Different types of them. After I get the output, post-process, a very important aspect. What kind of post-process I need? I need to get an idea what parameters I am getting, which is impacting my system. So as an engineer, I go through this process of post-processing analyzing the output data. Why it's important? This will give me the idea what kind of system I have developed or what kind of system I have, what is my modeling detailing is impacting or not. Because finite element is a method and simulation technique. It all depends the way you have modeled and used it. So that's why the post-processing data is very important for us. Here also verification validation is important. Between physical problem and mathematical model is validation is done. Whereas mathematical model and numerical model verification is done. These are very important aspects in ML. Some examples I'm showing. Actually, if I try to show the examples, it may run in 100 200 slides, but just glimpse of example I'm trying to show. Some of these examples I have worked personally and with my team. Okay, like example aerospace. The complete fuselage has been analyzed with the finite element method. If you look at the kind of loading, the structure, shape, and size, this is the. If you look at this, this is basically the wings part. The rear of the wing. When your landing time, your wing is extended, and how much thrust it is experiencing, and it's also showing the vibration, which is coming through the tire of the aircraft to the physical body. Turbo machinery, like these are the different types. This is an impact turbine, the Francis turbine. These are the areas where we look. If you look at this kind of turbines, this turbine generates, you will surprised to know, 135 megawatt power, single turbine. And this total weight is about 10.5 tons with the special states. And the impact speed of the water flow will be about 180 meters per second, which can actually slice off the human being in less than a second time in multiple pieces. Automobile, different aspect, very important aspect of the engine of the crankshaft, and this is a side impact. These are basically for safety purpose, this is for performance, enhancement of the engine, and this is for the power transmission, whether it's properly done, how long this gear system will be operating. And biomedical, the joint replacement, these are the inhalers which has been designed by us, and very important are lungs function, the heart lungs. Now these are ranging from hardcore engineering to biomedical. Sports, how many of us actually experience playing this kind of games, and we know if I hit the ball in such a fashion, it will get maximum output, maximum distance. Or hockey sticks, where do we hit? So this kind of applications have been done. Just a passing remark. Finite element has been used to actually design and develop a swimsuit which has given impact on reducing the time in Olympic arena. And they have been used for last almost 2 decades. Okay. Journey, how it happened. In 1940s, during the Second World War, this was the first development. As we grow in post this thing, it has been used by Boeing to start the work in 1956, most important aspect. And in 65, NASA developed, with 2 young people, a program called Astron for application space. 70s, it got developed into aeronautics, automotive defense. Present day, well, we can go from one place to another, including the physical applications. Everything has got advantages, disadvantages both. Advantages, it can readily handle very complex geometry. It can handle engine problems, wide variety. You take the problem and you can solve it now. Complex expense it can take care, and complex loading it can take care. At a time, all kind of loading comes into the system, or different kind of systems comes to picture, you can do that. But some disadvantages. General closed-form solution, which would permit one to examine system response to change in various parameters, is not produced here. It's open system. Second, it options only approximate solution. It is not exact. It has got some inherent errors and advanced areas. We discuss about these areas. And mistakes by users can be fatal. So a user has to be well defined, well trained. So what is this one? The basic 3 steps before we close down. 3 steps are pre-processing, processing, and post-processing. This is the field. In pre-processing, human, you is important. Machine, this computers. Processing is done by machine, post-processing machine plus human. So you start the problem and you finish the problem. So your importance is very important in this. Please do not blame the system or the process. Okay. So good modeling, simulation, and fine limit is possible when we understand our respective area properly. This is a general process of whole results. Overall method, user computer, pre-processing, computer processing analysis, these are the things which is being done in each stage and results are coming out. What can go wrong? Pre-processing stage, element type can, as an engineer, I can choose a wrong element, wrong coupling, wrong annihilation. Software can be. So this is developed by human being. We have to take care of this. Solution time also. Wrong calculation discipline. You are supposed to do thermal calculations. You are taking up the structural calculations. Wrong boundary condition. Wrong convergence criteria. This is a numerical simulation system. So your convergence criteria should be important. Post-processing, wrong result coordinate systems. Very important. In fact, we have seen time a dozen times the issues of this. So these are the kind of things can go wrong. So, but please remember, do not blame the system. We have to be careful. It's a typical FEA process, right up to production. The way we start up the whole thing. And this is what the FEA contributes in this. And FEA means it's both system modeling and system simulation. This is what we are, my friends. Modeling simulation FEM is the brain of engineering today. Today's world. In the world we live, better understanding and application of modeling and simulation and fundamental method will lead towards better engineering products and a balanced society. This is what I personally perceive as the things. And if you are more interested, we can look into these different aspects and situations happened last half a century. We appreciate what I made with sentence. Thank you very much for your kind attention. Rahim.
Thank you so much, Dr. Mahanty. It was really wonderful, and definitely it deserves a probably more discussion in the second part also. That is what we thought. Let us think of it in coming time. But thanks a lot for your today's deliberation. Thanks once again on behalf of your Budini and your